Yes, no. Can you have the same testing quality while running less QC? We'll go ahead and 64% said yes. Next, this is about your practice. So just think about when you run QC, when and how you run QC samples. Okay, 32% said at startup, at a set time during the day, and at the end of the day. And 25% said throughout the day according to testing volume. When an out-of-control condition occurs, the laboratory should retest patient samples since the last successful QC event. Oh, agree, disagree. Interesting. Gentlemen, you have good luck with your presentations. Oh. The overall cost, the overall cost of patient care can be reduced by increasing QC frequency. The overall cost of patient care. Disagree. More than half. Last question. What is the relationship between frequency of QC and Six Sigma? Or let's say the Sigma performance measures. Okay. You're still here. Only 4% have tuned out. So. Great. Okay, a little bit for tonight. We have our next two speakers. First is Dr. Niels de Jong from the Netherlands, who's been a part of us for the last several years. 2 years ago, led a group on how to, and having his work group really look at how to improve the laboratory standing in the continuum of patient care. How do we empower laboratorians? How do we put more sort of more value into laboratory testing? And last year gave us a really inspiring talk about musical interpretation, Mozart interpretation of quality control, which was fantastic. So we welcome you back.
Thank you very much. Dr. Curtis Parvin and I will address the topic of frequency of analytical quality control and the impact on the reliability of patient results. First, I want to thank the organizers for inviting me for this inspiring meeting. Well, Dr. Parvin is, without any doubt, an absolute expert in the field of statistical modeling of QC strategies. And he will share his ideas and his thoughts about this very interesting subject. And as he is mastering the subject much more than I do, I will focus on other concepts, but it will relate to frequency issues. Sorry, degree 1. Okay, so talking about frequency of analytical quality control, the question rises, why do we perform analytical quality control? And of course, we do so to assure that the patient result is correct. But analytical quality control is also a very good tool to control the testing process as a whole. Consecutive QC results within limits will give us some confidence that we don't have problem with an analyzer or a testing method. While on the other hand, if we have repetitive poor QC results, this will draw our attention to a particular testing procedure. Well, using QC samples to assure either the correct patient result or the correct testing process is a type of end control. And as I said, what's going on? It's not me. Are you so tired of... Can you switch that? Okay. Okay. Well, all right. Whatever. Well, as I said, Curtis Parvin will go somewhat further on the subject of analytical quality control. Well, I really missed the projection screen because I had a nice slide. He's trying over there. Well, meanwhile, I can explain you that a lot of work has been done on optimization of analytical QC frequency. And there have been studies published by Yun Pacheco and by Curtis Parvin and by Hachmi Hall. And recently in the last issue, or the one before in Clinical Chemistry, there was a very practical paper by Curtis about what to do with 2S rejections, a very practical everyday question in our labs. It is important to realize what is the background of our way of analytical quality control. And in its very nature, our analytical quality control is much the same as it was designed originally by Walter Shewhart in 1924. Walter Shewhart worked at Western Electric Company, telephone and telegraph company, and they faced problems with data transmission reliability. And if they did face a problem, they literally had to dig out cables, amplifiers, and other equipment. So you can imagine that this was a quite cumbersome situation and also a very costly situation. And Walter Shewhart came up with a very elegant way to notice whether there was a problem in the data transmission. This was the statistical process control, which we all know from the Shewhart chart. It was assumed that data from data transmission were distributed Gaussian, although Shewhart himself noticed that this was in fact not the case. but at least it was a better way to control the performance of data transmission than to have to dig out the cables and equipment every day and again. Well, the Shewhart approach was adopted to a clinical laboratory by Lever and Jennings in 1950. And the approach gained in specificity with the development of the Western electric rules around 1956. But that was still for telephone and telegraph performance, data transmission performance. And the Western electric rules are quite similar to the Westgard rules, which James Westgard published in 1981, and which most of the labs are using nowadays to interpret the Shewhart control chart. From the very beginning, with just a statistic approach of process control, there has been a great development in the application of tolerance limits, as we all know. Kotlov and others were among the first to realize that we had to take into account biological variation and analytical variation, and that it's more than just a statistical approach. And finally, the Stockholm Conference gave us guidance on the way we have to translate clinical goals into analytical goals. And much has been said already this morning by Callum Fraser and later this afternoon on Stockholm criteria, so I won't go into the details about this. Now, the next level of quality control is the quality system. And I'm sure that almost all labs will have some form of analytical quality control. Is this the pointer? Or this one? Oops, okay. So most labs will have some form of analytical quality control, and this morning we learned that almost all labs are being accredited or are busy to get their accreditation. And I have been working in accredited labs, or labs that have been accredited since the end of the 1990s for quite some long time, with fully implemented quality systems and extended analytical quality systems. But I still am struck by the reasons for unaccepted QC if you go into details of, and here we see the results of just one analyte and just a few months, maybe half a year, 5 months. And I looked at the reasons for unaccepted QC. And in our lab, every unaccepted QC is reported in the laboratory information system. So we know every reason for every unaccepted QC in every situation. And I would expect unknowns, and I would expect calibration errors. But apparently, there are a lot of, quote, trivial, unquote, reasons why QC is not accepted. In the last presentation, we learned the same for external quality assessment, the publication of Miller in Clinical Chemistry. I think we have to do something with that, and we can learn from other industries. We should improve our quality system with fault tolerance systems, as being done in the high-level software industry. We can learn from the pharmaceutical industry and use entrance control to prevent reagent problems. And we could adopt the total preventive maintenance ideas from the car industry. So apparently, having analytical quality control and having a quality system according to the ISO 15189 is not enough. And I will not go into the details of HACCP or risk analysis, but I would like to go into some more detail about inline process control, because I think that is complementary to analytical quality control. Now, what is an inline quality control? Inline quality control is a continuous, non-discrete control of process or product quality. Basically, there are 3 different techniques for inline quality control: measurements, as we do in our lab, data analysis, and fingerprinting or profiling. Well, for the last one, a very simple example is driving a car. You don't need to be a mechanic to understand that something might be wrong if the noise of your engine changes suddenly while driving on a highway. It's the profile which is changing, and that draws our attention, and we have to look further what's going wrong. Data analysis might be everything. That might be turnaround time increasing, or reagent consumption increasing, or whatever you can think of. And there are many examples in all types of industry, in the oil or gas industry, or food industry, or printing or textile industry. But here, I don't know for which reason, but this is an example from the beer brewery. And from clear water to beer, a lot is happening. All the ingredients are added and so on. Well, I won't go into detail of beer brewery. We might hear from it later on. But all the blue things, and there are over 30 points in this whole process, are inline process control points. And in beer brewery, they use UV visibility spectroscopy, osmometry, or infrared spectroscopy. And of course, they also take samples halfway or at the end of the process, and they test it in a very similar way as we do our analytical quality control in the lab. But because of its continuous and non-invasive nature, the inline quality control has a lot of added value. Well, we could do the same in the lab, and this is an operations research view of inline quality control in a clinical laboratory. We could look at different things. We could look at samples. We could look at reagents. We could have a look at our equipment, and we can look at the data. And for example, if you do a porphyria test, then it makes sense to make a UV-vis spectrum of the sample right after it entered the lab, but also just before you are going to start your analysis. If the UV-vis spectrum has changed meanwhile, you might think of an error occurred somewhere in the storage of the sample, for example. Well, in our lab, we are busy with studying the application of weighted moving average or moving median of patient results, and exploring all types of inline quality control in addition to our traditional quality control. So to conclude, that it's important to realize that statistical process as designed by Shewhart a long time ago is in fact a control of a black box process. And that gives us a need for complementary approaches. And I think inline process control is a very strong method to do so. But however, the proof of the pudding is in the eating. So we need to test or to check the end result of our testing. And analytical quality control in its traditional way will remain very important. Stockholm criteria have learned us a lot about how to set our tolerance limits, but I think there will be much more development in frequency and also in setting control rules. And our quality building is not finished yet. We have ideas, we have ambition, and on the left we see the Stockholm criteria finished already, but the inline control tower on the right is still being built, and it might take a lot of time, even centuries, and a lot of effort, but I think that in the end the result is great. Thank you very much for your attention.
Thank you, Niels. Next, it's my pleasure to present Dr. Curtis Parvin. Dr. Parvin has a PhD in biostatistics from the Washington University School of Medicine, and he wrote extensively there and for many years on the faculty. 3 years ago joined Bio-Rad, and he continues his QC research in his role in our R&D discovery team as Manager of Advanced Statistical Research. Dr. Parvin.
Thank you. So the last speaker of the last session of the day, right? Right. According to my watch, I have to finish in 30 seconds to be on time. One of my colleagues, to motivate me to not talk too long, said he was going to be sitting back there with a cold German beer that I could have as soon as I finished my presentation. So I'm motivated. Also, I think I'm going to hold the screen just to... Yeah. So I'm going to use this figure throughout my talk to try to motivate how we can relate quality control, planning, and design to the ultimate safety or risk of harm to a patient. This is kind of a redo of a figure that's appeared in the new CLSI EP23 document. So the idea here is the sequence of events that can lead to harming a patient or causing an unintended consequence in a patient. Some failure mode occurs somewhere in the testing process that leads to an out-of-control condition. Depending on that size and the type of out-of-control condition, that can lead to an unreliable, one or more unreliable patient results being produced, which may or may not lead to unreliable patient results being reported. At that point, the risk of reporting an unreliable patient result is kind of where our control of the process ends. That's what we can try to manage. And then there's some chance that an unreliable result that we report will lead to an incorrect action by a caregiver. And then there's some chance that that incorrect action might lead to an unintended consequence for a patient. I would argue that what we do traditionally in designing and implementing statistical quality control is what's contained in that green shaded area. We start with the occurrence of an out-of-control condition, and depending on the size and the type, there are a few types. We can think of an out-of-control condition that only affects a single patient sample, an out-of-control condition that affects a batch of patient results, an out-of-control condition that, when it occurs, will persist and continue to affect all patient results produced until we detect that there's a problem and do something about it. And an out-of-control condition could be of small magnitude or it could be of large magnitude. Depending upon the type and the size of the out-of-control condition, and depending upon what kind of quality control processes we have in place, some number of unreliable results will be produced. And depending upon how and when we report results, some number of unreliable results will be reported. The decisions we make about how we do quality control is all about managing that part of the process and trying to manage the risk of producing and reporting unreliable patient results, right? So if we're going to talk about the risk of reporting an unreliable patient result, we have to define what we mean by an unreliable patient result. ISO 15189 tells us that we need to assure that patient results meet the quality required for their intended use. So we have to define what that means to us. And a classic way of doing this, as we've heard from previous speakers, there are all kinds of quality indicators that we're concerned about. But for this purpose, the quality characteristic that's of primary concern is the magnitude of the difference between what we should have reported for a patient and what we do report. The larger that difference, the poorer the quality of the result. And one way that we can characterize that or quantify it is to look at the probability of producing a result that exceeds some allowable error specification. We've heard talks earlier about how to define allowable total errors or total allowable error specifications. So the idea here is that if we produce and report a result where the difference between what we should have reported and what we do report exceeds the allowable total error, we consider the result unreliable or incorrect. And if it's smaller then the idea would be that an unreliable or incorrect result has the potential to create a hazardous situation that might lead to harm to a patient. So it's, if we think of the shaded gray Gaussian distribution as reflecting measurement error for a process that's operating as intended, so the x-axis is measurement error. In this particular case, it's centered on 0, so we're assuming no inherent bias in the process. If we consider the dark Gaussian distribution shifted to the right as the state of the process because of an undetected out-of-control condition that's resulted from some failure mode, then we can compute the probability of producing a result that fails to meet its intended use by determining the area under that curve that is outside of our allowable error specification. And in fact, we can do that for every possible magnitude of out-of-control condition that might occur, and we can generate a curve that looks something like this. So P subscript capital E here is meant to represent the probability of a big E, a big error condition, so probability of an unreliable result. And we can see that, and the x-axis is the true state of the testing process. So a value of 0 here means the process is in control, and a value of 1 here means that there's been a systematic shift in the process that's equal to 1 analytic SD of the process. We would expect that if we have good testing processes, that the chance of producing unreliable results when the process is operating as intended should be very, very low. So we would expect that this curve starts out at a value that's very small when the process is in control. And certainly for large enough out-of-control conditions, the probability of producing unreliable results can approach 1. Okay. So that's the way we'll define and quantify the risk of reporting, of producing and reporting an unacceptable or unreliable result. Now, the key outcome measure that I'm interested in to try to relate what we do in the laboratory in terms of quality control and the risk of harming a patient is the expected number of unreliable patient results that will be produced in the event of an undetected out-of-control error condition. So in this cartoon, which appears in a lot of the figures that in papers that I've published recently, the horizontal line is meant to represent time. Each individual little vertical line is representing a patient specimen that's been tested, and the diamonds represent the points where we test quality control and make a decision about the state of the process. If the diamond shaded green, that means that our quality control rules conclude that the process is operating as intended, and if it's shaded red, that means we get a QC rule rejection. Okay? So the idea here is we're going along, we're in control, and then at some point in time, failure mode causes an out-of-control condition that results in a shift in the process, so that on average we're producing results that have a constant bias in them. The number of unreliable results that will be produced during the existence of that out-of-control condition will depend upon a number of things. It will depend upon the type and the size of the out-of-control condition. That will determine how many of those vertical lines have a red asterisk above them. The red asterisks are meant to denote those patient results that are unacceptable, that are unreliable. The larger the size of the out-of-control condition, the more of those vertical lines we'd expect to have red stars above them because it's a larger error condition. It's also going to depend upon how good our quality control rule is at detecting the out-of-control state, the power of our quality control procedure. The more powerful the rule, the fewer tries it should take before we detect that we have a problem. And then thirdly, the thing that the focus of this talk, the number of unreliable results produced during the existence of the out-of-control condition is going to depend upon how frequently we test QC. If we test QC, if we have more patient specimens between QC events, they're more likely to have, we're going to have more red asterisks during the extent of that process, right? So, we've seen this slide before, and now I've added in the right column ENU, which is, I didn't specify, it was in the title of the last slide. That's what I used to represent the expected number of unreliable results that were produced because of the existence of an out-of-control condition of a certain size and magnitude, or a certain type and magnitude. So what we do when we're defining, or what we can do when we're defining our quality control strategy is ask, given this quality control strategy, given these rules and this frequency of testing, what would be my expectation for the number of unreliable results that would be produced during the existence of an out-of-control condition of a certain magnitude before I detected it? Okay. Now, how many of those unreliable results that are produced end up being reported and potentially causing harm will be dependent upon how quickly we detect the condition and when we report results. So, go on. Now we're told, again, the things that, there are three things that can determine how many unreliable results are produced and reported, which is the magnitude of the error, which we don't have any control over, the quality, the power of our QC rule. That's the thing that we typically tend to look at, is how powerful is our QC rule, and the frequency of QC testing. And this session is on frequency, so that's what I'm going to focus on, not the others. And we can think, when frequency of testing is really all about when do we schedule QC. And we schedule QC two different ways in the laboratory, which I refer to as event-related QC and an event-independent. So the idea with event-related, as was alluded to by Niels, is we understand that there are certain critical control points in the process where we may be concerned that a change can occur because of that critical control point. And we want to test QC to assure that something hasn't changed at that point. I call that event-related QC testing. The frequency is determined then by those critical control points and when they occur. We don't determine that. That's determined kind of for us. In those cases, we almost always will test QC immediately after that critical control point to assure that something hasn't changed. I would argue that that's a legitimate thing to do, and that the focus of that is really an instrument focus. We're concerned about the instrument, whether or not something's happened to it. I would also argue that you should be, when these critical control points are known in advance, you should be testing QCs immediately prior to that event. I would say that's a patient focus. The idea there is that I want to test QCs to assure that all the patient results that have been produced and reported since my last good QC are reliable. Okay. In fact, this was one of the recommendations that came out of one of the working groups from last year's experts meeting. And it appeared in the opinion paper, which is that QC testing should not only follow calibration, but should immediately precede calibrations, just for this reason. If our focus is going to be on the patient, one of the previous speakers said, our focus should be on the patient. If our focus is going to be on the patient, then we really need to be testing QCs prior to critical control points that might change the process, as well as immediately after them. I'm not really interested in event-related QC for this talk. I'm interested in what we do between those critical control points. How do we decide when to test QCs between those critical control points? What frequency do we use? Now, you can think of frequency in two ways. Time, I'll test once a day, I'll test once every 8 hours, or the number of patient specimens between QC events. From the perspective of patient risk, it's the number of patient samples between QC events that's the critical key, not time. Now, when we detect an out-of-control condition, ISO tells us that there are some things we have to do. We have to halt the process. We have to take corrective action. And then any results of non-conforming examinations that have already been reported need to be appropriately identified and corrected if possible. As I'll call this recovering from an out-of-control condition. So if we go back to the cartoon I looked at before, we can think of that period of time where the process is in an out-of-control state and break it into two intervals. That section that was from the occurrence of the out-of-control condition up until the last QC event that passed. They gave us an acceptance signal, and then the interval from the last good QC to the place where we detected it, where we got a QC rule rejection. I refer to the first as the pre, and the second is the post. Pre-last good QC event, post-last good QC event. The idea here would be if we're holding results and releasing them only after we get an accepted QC, then that post period would never get reported. There would have been unreliable results that were produced, but they would have never been reported. Okay? If we're immediately reporting results as soon as we get them, then what ISO and others would say is that those results, at least back to the last good QC event, are the ones that we should try to identify and correct. And if we can do that in a timely fashion, then we can think of that as a result that wasn't a final incorrect result that was produced. So now we really have, in terms of looking at the influence of frequency of testing on the risk of producing an unreliable result that might cause patient harm, we kind of have the conceptual model that we need. It's not a difficult conceptual model. I've heard people talk about how, yeah, we recognize now that frequency of testing is an important issue, but that's a complicated topic, and some people are working on it, but we haven't figured it out. It's really not that complicated. Conceptually anyway, it's not that complicated. The number of patient samples between QC events are going to influence how many bad results get produced when an out-of-control condition occurs. Okay? Now the question just becomes, can we predict or compute or estimate what the implications are given a particular quality control plan in terms of what it implies for the risk of producing unreliable results that were prior to the last good QC event, which means they probably are incorrect, unreliable, have gone out and will never be corrected, and those that have been produced since the last good QC event, which maybe never get reported, or if they did get reported, maybe can be corrected before they cause a hazardous situation that results in harm. Well, it turns out computing the things isn't that difficult. It's not a lot any more difficult than computing a power function graph. Not that all of you go out and compute power function graphs every day, but there's nothing really any more complicated about the mathematics or the simulations to compute these things than is required for computing all the power functions that are out there in the literature. So here's an example. The top figure shows two curves. The blue curve on the right is one we've seen before. That is representing the probability of producing an unreliable result in the presence of an out-of-control condition of a given magnitude. Okay? That curve depends upon our total allowable error specification and the performance characteristics of our method in precision and bias. Okay? So we can't compute that curve without specifying an allowable total error. The green curve on the right is reflecting on average how many patient samples are produced while an out-of-control error condition occurs up to the last good QC event. That curve is going to depend upon the answers to the three questions of what rule, how many QCs do I test for the rule, and how many patients do I test between QC events. Okay. So because it's the average number of patients produced, it's a number that for very small out-of-control conditions is going to be large because it's hard to detect very small out-of-control conditions. And as the out-of-control condition gets larger and larger, the chance of us detecting it the first time is high. If we detect it the first time, then there are no unreliable results prior to the last good QC event because there were no unreliable results produced prior to the last good QC event. The product of those two curves, how many on average results were affected times the probability that they're unacceptable produces the lower curve, which is the expected number of unacceptable results that were produced prior to the last good QC event as a function of the magnitude of the out-of-control condition. Now, we don't know what magnitudes of out-of-control conditions might occur in the future, but if we look at a curve like this, what we could say is if for this particular situation with my allowable error specification, whatever it is, and my QC plan, whatever it is, I would never expect more than 2 unacceptable results to have been produced prior to the last good QC event. Okay? So that gives me some knowledge that I can use to try to manage things. The expected number of correctable unreliable results is the expected number since the last good QC event, so in that last interval. And here things aren't quite as nice. This really is mostly a function. So again, the blue curve is the same as in the last figure. The green curve is the average number of patient samples that were affected by the out-of-control condition since the last good QC event. And it really only ranges from the total number since the last good QC event to half of that. So in this case, I must have been assuming 100 patient samples between QC events. Okay? So when you multiply those two curves, you get something that starts low, increases, and flattens out at a value that's 1/2 the number of patient samples between QC events. So this number, this correctable number, is really simply a function of the frequency of testing. The scheduling of QC doesn't really have too much to do with the power of the QC rule. So I've added another symbol to the right on this figure. So we can compute for a given QC plan for different magnitudes of out-of-control condition for different types. So the only type I've looked at here was a persistent out-of-control condition. We can compute the unreliable results produced, the expected number. That was the total number of red stars. And we can also compute the expected number that were part of the last good QC event. Those were the ones that would most assuredly have been reported and probably never corrected. If we're doing bracketed QC, that would be it. If we're doing immediate release, it might be somewhere between ENUF and ENU, depending on how many of the unreliable results since the last good QC event got corrected in a timely fashion. Okay? This is the thing that we can try to manage. We can decide on a QC plan to try to assure that the expected number of unacceptable final results doesn't exceed a value that we're willing to tolerate. Now, what value are we willing to tolerate? Okay, well, that's going to maybe depend. It's going to depend maybe on what our information or assessment is of the likelihood of an incorrect result resulting in patient harm. We don't have control of that part of it, but we can certainly be informed about it. So if our assessment is that this is a situation, this is an analyte used in a particular situation where if we produce and report an incorrect result, it is most assuredly going to lead to patient harm, then we might want to manage that expected number of incorrect results that we report at a much lower level than another situation where our assessment is that, you know what, we could produce and report 100 incorrect results, and maybe only in one of those 100 cases will we expect it to lead to harm to a patient, in which case we might be willing to tolerate more unacceptable results being produced and reported. What I'm trying to say here is that I don't want to tell you what that should be, but it's not like there should be a one-size-fits-all. You really, as laboratory professionals, should have some input into how to manage that number in a way that makes sense for the analyte and the patient population that you serve. Okay? So my last slide. So quality control is needed. Why? Because clinical diagnostic processes fail. We are the instrument manufacturers with risk management and with risk management guidelines in the laboratory. We're doing a better and better job of trying to identify potential failure modes and reducing their occurrence. But when it's all said and done, our processes fail. Okay? And we need quality control because of that. The impact of process failures should be assessed in terms of the risk of reporting unreliable patient results. I wrote a paper last year in a journal called Advance, where the title was that quality control should focus on the patient, not on the instrument. I think for too long we tend to focus on controlling the instrument. We're controlling it with an understanding that poor performing instruments lead to bad results that might affect patients. But our focus should be with the end in mind. We should be focusing on the patient and then determining how to control our instruments in a way that assures that the risk of producing and reporting unreliable results is low or is manageable to a level that we're comfortable with. The frequency of QC testing, the number of QCs examined, and the QC rule all impact the expected number of unreliable patient results that will be produced during an out-of-control condition. You can't ignore frequency. Number of controls and the control rule are fine for determining how likely you are to detect an out-of-control instrument, but it's not enough for determining the risk of producing and reporting unreliable patient results. You need to know the frequency also. It's not only possible, but it's not all that difficult to design QC strategies to manage the expected number of unreliable patient results that are produced and reported when an out-of-control condition occurs. And what's considered acceptable should probably depend upon our assessment of the failure mode rate and the likelihood of patient harm resulting from an unreliable patient result. And with that, I thank you for your attention. Wait, hang in there, and I'll be back for my beer in just a second. Thank you.
Okay, we have time for just a few comments, questions, if anyone has them. This is our last group, and then we'll be going to a group photo. I just had one thing, Kurt, in your last thing about harm to patient and the evaluation that the lab would have to do about what would constitute a harm to patient. How would you go about beginning that process?
Well, again, I think most laboratory professionals, most clinical pathologists, they know the likelihood of an incorrect troponin leading to harm is different from the likelihood of an incorrect cholesterol. And then I don't even think it should be, depending upon your laboratory, are you a reference lab, are you an acute care facility, are you a physician office lab, how particular analytes are used for diagnosis and treatment in your patient population might differ also. But at least in my experience, of course I was at Washington University, which is they're quite opinionated there, but there was no shortage of opinions about what they thought the quality needs were for their results based upon their knowledge of how those results would be used for patient care. So does anybody disagree with that? Or is that something that would be difficult for you to all assess? And it's, all of this stuff is more of a guide. Even, the curves that I show with the expectations and predictions, those are only as good as kind of the modeling that we do, but it certainly is a more robust, richer way of looking at the problem than we classically do. And that would be the same way. That would just get you closer to maybe what you're really shooting for if you're making an assessment for the likelihood of an incorrect result reported by your laboratory resulting in patient harm.
Is there a, yep.
Please, yes. Congratulations for your presentation. I'm Florian Scherer from France. And I would like ask you, do you think the concept of average of patients, average of normal patients, can contribute to reduce the frequency of internal quality control? Because it's not a very expensive quality control, and I'm sure it's relevant in many cases.
I'm a big proponent of using patient results as part of a quality control scheme. I published a paper in American Journal of Clinical Pathology in 2000 or something like that on patient-based average of normals. I think that it's underutilized because I think it's gotten a bad rap in terms of the way it's been evaluated in terms of its opportunities for improving things. And we're actively pursuing, I'm still actively pursuing approaches to using patient results as part of a quality control system. Not to replace routine quality control. Certainly now that I'm working for Bio-Rad, I can't propose replacing routine quality control, but as a supplement to quality control. Because one of the things you realize as you start looking at frequency of testing, you recognize that one of the inherent vulnerabilities of any QC process that's only based on the periodic testing of control material is that it's the time between the occurrence of the out-of-control condition and the next scheduled QC event. And it doesn't matter how good your QC rule is, there's no way of detecting it until you test it. And so one of the advantages of patient results is that it gives you the opportunity to assess the state of your process with every new patient result. You're getting a very little bit of information from each patient result because of all the biologic variation in the results. But as long as the information can accumulate to give you evidence before your next scheduled QC, it benefits you. So now we can get into long discussions about how to go about designing a patient-based quality control plan well, but I do think that, in fact, you're seeing more and more discussion and interest in patient-based QC, which I think is a good thing for the field.
If I may add to that, well, the concept is already known for quite a long time, but just recently we got the possibility of calculating averages or moving averages or moving medians of patient results within our laboratory information system. And that gives us the tool to explore the measure further on than the known examples such as electrolytes, etc. So I think we will come to new applications of an old concept.
Good. Okay, and Niels, I look forward to, if a brewery happens to be in our evening plans, I look forward to participating in some inline quality control with you in that.
Well, in that case, I prefer end control.
Okay, Gianni?
One communication, logistic communication. At 6:30, we have the guide for the city tour. You already are split in 6 groups. You have in your folder. And now when we exit the room, there is a photographer at the reception to take a picture of all of us. There is some steps going down just aside to the reception, all together. And then only with the speakers. So the others are free to go to the room before waiting we are for the guide. And we take a second picture with the speakers. Only the speakers. Okay. So if you don't mind to go to the reception for the picture, you return and don't forget to return the device at the end of the room.
Right. And